Hello, class. So we continue with our lecture on production of power from heat. So last time we discussed how to increase the efficiency of the Rankine cycle. There are two ways to increase the superheating or the temperature in the before the steam enters the turbine. And the second way is to increase the pressure in the boiler. As the pressure in the boiler increases, the temperature also increases to unsafe levels, and it will entail high costs for the boiler and superheater. If the boiler's pressure is increased, the quality of the exhaust steam decreases. So it increases the thermal efficiency, but it also increases the moisture content to unacceptable levels, thus it will cause erosion problems. Therefore, in actual power plants, uh, they seldom operate above 10,000 kilopascals and above 600 degrees Celsius. And then we also discuss the version of the Rankine cycle with superheat and reheat. This time, the Rankine cycle is modified by reheating the partially expanded steam, and it's composed of two stages. The expansion is composed of two stages, the high pressure and low pressure stages. This is the diagram for that. Uh, so in the middle of expansion, steam is extracted and reheated in the boiler. And then again, it's sent to the turbine again for a second expansion. So first, the high pressure superheating, and then uh, it will the steam will partially expand and then go back to the boiler for a second reheating. And then expanding again. So the first stage is the high pressure. Remember, this is an isobar, and this is a higher pressure than this one. So this one is the lower pressure superheating. So the effect is that, as you can see, uh, the expansion, um, the final expansion is now nearer the saturated vapor curve. Therefore, the quality is higher, and thus increasing the overall efficiency of the cycle. So let's consider this sample problem. A steam power plant operating on the reheat Rankine cycle. Steam enters the high pressure turbine at 10,000 kilopascals and 600 degrees Celsius. After reheating at a low pressure of 2,500 kilopascals, the steam enters the low pressure turbine and exhausts at 10 kilopascal. So if the efficiency of the turbine is 80% and the efficiency of the pump is 75%, determine the thermal efficiency of the cycle. So let's try to solve that. Okay. So what's the first step again in solving these types of problems? We draw the TS diagram. Okay, let's draw the TS diagram of a Rankine cycle with uh, superheat and reheat. Oops. TS, then we have the saturation curve right here. Okay, and then we draw the Um, oops. The boiler, then the oops, then the first heat superheating, the second, the first expansion, and then okay, the second superheating. So just imagine that this is a straight line towards the saturated liquid curve. Let's label the points. Let's label this as E, F, G, and then this one A, B, C, D. Okay. So notice that we usually label points. Usually label. Alright, so this one, the boiler, it's arbitrary. The labels are arbitrary. Anyway, let's use this. Okay, what is the given? Given given information are uh, at point A, point A, hold on, let me go back to the steam enters the high pressure return. Yeah, point A. So the pressure is 10,000 kilopascals. And then temperature is also given. TA is 600 degrees Celsius. And then there's reheating. Okay, so where do we place the reheating? Okay, so the pressure here, right here, is 10,000. In the reheating, it's point B. The pressure here, so PB is 2,500 kilopascals. Okay, so what else is given? Um, the final pressure at the exhaust. So that's PD. Okay, so PD is 10 kilopascals. And we're also given the efficiencies of the turbine and pump. Okay, the efficiencies of the turbine and pump, which are 80% for the turbine, and for the pump, it's 75%. And we're being asked for the efficiency of the cycle or end cycle. We can label that as or just simply N. So let's go back to the equation for the efficiency. So remember, um, equation of the efficiency is the work net. Work net over QH, and the work net is the work of the turbine plus the work of the pump over QH. And this is equal to if work of the delta H of each And since MFS is available in both, yeah, so let's write the formula from our energy balance. Okay, and where MFS will cancel from the numerator and the denominator. The work of the turbine, there are two. Okay, there. So for the turbine, there are two. So that is HB minus HA plus HD minus HC. Correct? HB minus A. So, dalawa yung turbine expansion, this one and this one. My, plus, okay, work required by the pump, HF, HF minus HE. Okay? So, this is the first expansion, second expansion, and this the work required by the pump. Alright. So, how about for QH? So, QH, there are also two steps. Um, it's There are two steps. So that would be HA minus HF plus, so ito yun, okay, the first uh, heating, and then we have reheating HC minus HB. Correct? Let me see. Okay, so now we'll try to solve the problem. Um, so we begin at point A where it's superheated steam. So superheated steam PA is 10,000 kilopascals and the temperature is 600 degrees Celsius. So uh, HA is 3,622.7 kilojoules per kilogram. SA is 6.9013 kilojoules per kilogram. Okay, so that's about the data that we can get. Next is point B. Okay, what's point B? The high pressure turbine. The high pressure turbine outlet. High, oops, high P turbine outlet. Okay. What do we know here? PB is 2,500 kilopascals. And so let's assume isentropic expansion. So S B prime, so it's a vertical line. Okay, let's correct so this is isentropic expansion. But this one right here, this is the actual B. So this one is the isentropic expansion, the vertical line. The slanted line on to the right is the actual expansion. So make sure that it lies uh, on the same horizontal line as the first. Okay. No, actually, it should be not on the horizontal line, but right here. Right here. Okay, so just let's correct that. Because it has to be, so this is B prime and this is B. because it has to be on the same pressure, 2,500 kilopascal, on the same isobar. Okay? Now let us check. Okay. So this value is 6.9013. Correct? Uh, so you can, so by the way, we don't know the temperature for that. You don't know the temperature for that. See, it's on a different temperature. Okay. Um, so how do we get HB prime? How do we get HB prime? It's not available. We cannot read it directly from the steam table because we only have one parameter here, the pressure, 2,500 degrees, 2,500 kilopascals. And we need another known parameter. So we can use actually the entropy. We can use the entropy to interpolate for HB prime. Okay, so using the steam table, interpolating from the steam table, HB prime. So I assume that you know how to interpolate using 2,500 kilopascal that data, and using the entropy we can interpolate HB prime, and that is 3164.47. Okay, so please do this on your own um, at home. So our next, so we know HB prime. What's the next step? We use the efficiency to calculate for HB. So remember what's the equation of the efficiency of the turbine? It's uh, delta H. Ano ba yung lower? Delta H. So, ano yung nasa ilalim? Pag turbine, ang nasa ilalim ito because this is the larger value. Okay. And this is HB minus HA, HB prime minus HA, right? So, plugging in all the values, you can get HB. So, meron na to from step A or point A. Then we have HB prime interpolated from the steam table. So, HB is 3256.116 kilojoules per kilogram. Okay. Next, at point C, this is the reheat. Reheat. What do we know? PC is 2,500 kilopascals. Why? Puntahan natin. PC. Diba? Ito yan. So, it's an isobar. So, PC is equal to PB, 2,500. And what about the temperature? So, pantay siya dito sa point A. So, they're on the same temperature line. So, PC is equal to TC is equal to TA. Okay, gets? T TC equal to TA equal to 600 degrees Celsius. We can easily read from the steam table. From the steam table, HC 3685.1 and SC 7.9. 7.59. 0.56. Okay. Next, we move on to point D. Ano yung point D? Saan na tayo sa steam? Ayan, nag-expand na siya in the low pressure turbine. So, it's the low pressure turbine. Let's label that. So, we know from the given, point D is 10 kilopascals. Since it's already inside the saturated curve, therefore, automatically we can read TD from the steam table, and it's 45.83. The saturation temperature at this pressure. Okay, so we can read SDL 0.6493 and SDV 8.1511. So from the steam table. So bakit natin kailangan yan? We will assume an isentropic expansion. Okay. So therefore, SD prime, diba? We assume an isentropic expansion. SD prime is SDL times 1 minus x prime plus SDV times x prime. Plugging in all the values, we know SD prime is just equal to, lagay ko dito, SD prime is equal to SC. Ano yung nasa taas? SC, right? So, this one is this is D prime. Okay, so this is D, this is D prime. So it's SD prime is equal to SC, and that's equal to, ayan yung value na yun, 7.5956. Plugging in all the values, we can solve for x prime, and it's x prime, and it's 0.92595. Okay, so just to differentiate, itong x prime na to, yeah, so x prime, it's the one that's inside the saturated vapor curve, right there. Okay. Ito lang naman pala yung x na pumasok sa loob ng saturated curve. So, next, from there, we calculate HD prime. But first, HDL is 191.832 and HDV is 2584.8 from the steam table. And therefore, using x prime, HDL, HDV, we can calculate for HD. Okay, it's 2407.6034. Okay, bakit? Diba HD prime is just HDL times 1 minus x prime plus HDV times x prime. Okay, so kayo na mag-fill in the blanks. Next step, okay. So may HD prime na tayo. We're given of course, we know the efficiency of the turbine, low pressure turbine. So, again, just like what we did here sa taas, yan, calculate natin yung HD. So, again, what's the equation of the turbine? Delta H or delta HS. So this is Yung nasa taas, HD minus HC over HD prime minus HC. So, all of these values, meron na tayo. Therefore, HD is, what's HD? 2663.10 kilojoules per kilograms. Okay? So, just to um, calculate the work done by the turbine, the two turbines. So it's HB minus HA, not HB prime, plus HD minus HC. Okay? Plugging in on the values, you will get negative 1388.584. So why negative? Because it's work done by the system or the cycle. Okay, so let's proceed to point E. What's point E? Saturated liquid. Saturated liquid, what's the pressure? So PE equal to PA equal to 10 kilopascals. Um, so from the steam table, um, HE is saturated yan. So 1 equal to 191.832. And then VE is 1 point, so na-convert ko na, 0.00101 meter cube per kilograms. Na-convert na. So, meron na tayong HE. Ayun, nasa, ayan. HE, di ba? Saturated liquid. So, nabasa agad. Let's go to point F. Subcooled liquid. Subcooled or compressed liquid. Subcooled. So, nasa labas na siya ng saturation curve. What is the pressure? So, nasa ano na siya eh, entry ng boiler. Okay, boiler. So, isobar to, PF equal to PA. PF equal to PA equal to 10,000 kilopascals. Okay? So, remember, for the isentropic pump, delta HS is VE PF minus PE. Remember, um, we derive that equation. So therefore, plugging in the values, we have VE, PF, and PE. Delta HS is 10.0899. Okay? So may delta HS na. So what's the significance of that? So this is the isentropic delta H. Therefore, for the pump, ano yung equation natin? Delta HS ang nasa taas, delta H ang nasa baba. Correct? And this is, ano yung pump natin? F, E at F. So, kung nasa taas ang, so this, tama, HF. So, HF prime to. And then, ito yung, okay, tama. So, Mas maliit kasi yung mas malaki yung work required pag actual kaya mas malaki 'to. Okay. So we have all the values. Yeah, we know ito 'yon, delta HS. So we know that. And then ito yung unknown. We know HE from here. Okay. So makukuha na natin yung solving for HF actual. It's 205.2852. Okay, gets? Next is do we have everything? Ayun, we have everything already. Pero let's calculate for QH or Q in. Q in is QH. Right. So remember that it's HA minus HF plus HC minus HB, diba? So we have everything now. Plug in all the values. That is 3846.3988. Now we can solve for the efficiency of the cycle or N times 100. Let's work net over QH. So work net would consider the work of the turbine and the pump. Okay. So just plug in all the values. Kanina we calculated for the work of the turbine. So uh just add the work required by the pump, which is, by the way, wait lang, positive. Positive siya. So, asa na yung pump? Ito, positive siya. Okay. So, subcalculate nga natin dito. Work required by the pump is kasi, diba, it's delta HS divided by the efficiency. And which efficiency is 0.75. Okay. 13.4532. So, ito yung work ng turbine, which is negative 1388.584. So, opposite sign dapat sila, no? 4532. Opposite sign sila. Then over QH. 3846.3988 times 100. So, you will get 35.75%. Which is higher than last time, di ba? Although iba yung operating pressure and temperature nung last problem, but this is relatively a good value. Try natin, what if compared to cat? Yan yung answer. What if Carnot? For a Carnot operating in the same pressure, temperature. Makukuha mo dyan ay so yung low temperature ay 45.83. So, plus 270.15. Tapos, yung sa ilalim ay yung high, Carno. Teka. Ano dapat? So, ito yung Carno. Dito nag-ooperate. Okay. So, dito yung Carno. So, hindi siya, ang temperature niya hindi 600 degrees. Kasi ito yung 600. We should get, okay, the temperature at this point. Okay, but we can do that using the steam table. So, kaya nang tumingin sa steam table, pero ang value niyan, okay, so again, this is the low temp do sa Carno. And then, ang temperature nun ay 318.96 plus 273.15. Okay, gets ba kung paano? And tapos, all of these times 100, ang efficiency ay 45.39% pag Carno. So, what if there is no reheat? Sige, to be continued yan sa next lecture. What if there's no reheat?